Bismillah ar-Rahman ar-Rahim. This is Dr. Ahmad Al Faris. Today we are going to start Edexcel Unit 2 to talk about the first topic, the introduction about waves, okay, and nature of light. Today we'll talk about the waves properties and what is the relationship of the properties of the wave and how we are going to use them together, okay, to answer past papers questions about Unit 2 Edexcel. And as you know, okay, from the previous years, or if you did Unit 1 the last semester, okay, usually Edexcel, they try to mix ideas or questions together. Some questions, they are easy, other questions, they are hard. And eventually, the last 2-3 questions, they have a lot of marks and a lot of ideas that they are mixed together. But in Unit 2, it's not similar to Unit 1. There is no trick, a lot of tricks in these questions. They in this topic, they are direct, they are easier, and they keep repeating the same ideas, not as Unit 1 that you studied before or in last semester. Unit 1 has a lot of ideas that they can mix it and make the question not clear, and you don't know which way or what is you are going to do and how you are going to solve the question. But counterclockwise, okay, on the other hand, okay, we have Unit 2, which is much clearer and easier, and you can get a good mark for it and maybe full mark, okay, and A eventually for the whole thing, Edexcel AS. Unit 1, Unit 2, and Unit 3, inshallah. Most of the students, they do a lot. They get a high mark. Okay, they do much better in Unit 2 than in Unit 1. Okay. Okay. So first of all, let's say Bismillah. First of all, okay, what do we have here? Okay, this, as you can see, it's an introduction about what we're going to study in waves. In waves, we have non-particle waves. Okay, and we have particle waves, and usually they talk about electrons when we talk later about something called de Broglie wave. Okay, that talks about electrons. Okay, non-particle waves, we have to talk about two types of waves here. The standing wave, the most important thing that it's new for the students. They didn't study it in the previous IGCSE, or that's the first time how they ask about standing wave. What's the meaning of standing wave? They usually put it on a musical instrument. Then we are going to talk about progressive wave and how the progressive wave, they change, how they transfer the energy, and we can divide it in several categories. First of all, according to the need of medium, that's why they call it electromagnetic waves, like light. Okay, or they call it what mechanical waves that needs a medium, like sound. The other types of the other category of progressive waves, or any waves, they can be according to the direction of vibration. As you heard before, they call transverse and longitudinal wave. Okay, transverse usually vibrate perpendicular to the direction of the wave propagation, while longitudinal vibrate parallel to the direction of the wave propagation. So let's start from beginning. I want from you to send me the chat about the ideas that you know it. Okay, who can give me examples about electromagnetic waves on the chat? If you please send me electromagnetic waves. If you know, give me examples. Thank you. One of the answers is ultraviolet light. Another answer. Radio waves. Thank you. Okay, who else? Okay, X-rays, excellent. Tamam. Okay, gamma rays. All these are electromagnetic since they are from the electromagnetic spectrum. They have electric field and a magnetic field. Infrared, exactly. Okay, tamam. Okay, now who can give me examples about mechanical waves? Who can give me examples about mechanical waves? The wave that need a medium to transfer from region to another region. Okay, thank you, Hamza. Okay, Hamza says sound. Light, it doesn't need a medium. So yes, exactly. Amira, repeat the answer. It's sound waves. Excellent. Water waves, also they need a medium. If there is no water, there is no water waves. What about something that shake the ground? What we call it? Spring wave or slinky spring waves. Yes, thank you. That's another example for mechanical wave, because if there is no slinky spring or there is no spring, there is no. Excellent. Seismic waves. We have seismic wave, the earthquake waves. These types of waves, they need a ground or water. If there's no ground or water, there is no tsunami and there's no earthquakes. Thanks. That's it. Okay. Now let's go back to what? To transverse wave. Who can give me examples about transverse wave? Like what? Examples about transverse wave. All this information you have to know it from since the IGCSE. Who can give me examples for transverse wave? There's many examples. Exactly. One of the answers, one of the girls should send me the whole answer. I will not say it now. I'll say it later on. Okay, transverse wave, like what? Who can give me examples? Send me on the chat if you please. Give me examples. Exactly. Okay, yes, water waves. Bravo. Water waves as they shake or they vibrate, ripples or up and down. Okay. Also the tsunami waves. Okay, excellent. What else? Radio waves. That's an accepted answer. All these answers are accepted for the transverse. Why? Because the wave is moving forward, but the vibrations are vibrating up and down. Another one, give me the correct answer. All the electromagnetic spectrum, okay, they are vibrating upward and downward. Vibration of the guitar, excellent. It's a transverse wave also. Tamam, light wave, electromagnetic waves, microwaves, radio waves, all these, they vibrate up and down. Thank you. Who can give me examples for longitudinal waves? Who can give me examples for longitudinal wave? We have a unique example. Okay, that's every time we, yes, thank you. Many answers I saw here. Sound waves, all types of sound waves, ultrasound, infrasound, all types of sound waves, they are longitudinal wave. And there's one type of seismic waves that it's what? It's longitudinal. Yes, exactly. So we have to know that NB usually you saw it in the mark scheme and it's a Latin, okay, or Italic language. Nota bene ملاحظة هامة, important note, nota bene. In both transverse or longitudinal wave, the particles vibrate about a fixed position. Okay, so actually when you are in the water and the water wave pass through you, you vibrate or oscillate up and down, but the whole wave keep moving, okay? The same thing for Mexican wave, the people on the stadium, okay, if they start to move their hands up and down as the wave pass through them, the wave keep moving, but they only vibrate up and down. The same thing for air molecules while you are speaking, okay, the air molecules, they keep vibrating forward and backward and the wave keep moving forward, but not the particles move a lot forward. They only shift a small distance, which is called amplitude. Energy transfer from the source, not matter, okay? And waves that travel from one end to the other, they call it what? Progressive wave, not standing wave, as we are going to make it more clear later on, okay? So waves, as you know, they are vibrations. They are vibrations, transfer what? Transfer energy, okay? For progressive waves, they transfer energy. And we have two types, okay, according to what? To the need of medium. Need of medium, okay. This is Edexcel, yes, this is Edexcel. Mechanical wave, okay, and electromagnetic. We are going to talk about Edexcel, but actually this topic, it's merged in both Edexcel and what? Cambridge, in both AS level. It's included in the syllabus, okay? You are welcome. So mechanical waves are the waves that need a medium. So waves need medium. And whenever the medium is denser, what will happen to the wave speed? Whenever the medium is denser, what happens to the wave? They travel what? They travel, whenever the medium is denser, they travel what? They travel faster, okay? They travel faster. Why they travel faster? Because, for example, sound, okay, whenever the molecules are closer, the wave travel what? Much faster, because the medium is denser. For example, sound cannot travel in vacuum. بسم الله الرحمن الرحيم فلا يسمع لهم صريخ ولا هم ينصرون. In the space, no one can hear anything, okay, without a special instrument that they put it on your ears. For example, the explosions of the sun, we can't hear it because there is nothing between us and the sun. It's empty space. So that's why we can't hear the explosions of the sound. So whenever the medium is denser, that means the molecules are closer, that the wave travel what? Faster, okay? Since molecules are closer. Molecules are closer. And a unique, the most important example about this, okay, is sound, okay? Sound waves, they travel what? And there's others, okay? Sound waves, they travel faster through denser mediums. So they travel faster through steel than through water, and they travel through water faster than in air, and they don't travel through vacuum and etc. Okay? Tamam. So electromagnetic wave, okay, it's the opposite, okay? It's not the wave that need a medium at all. They don't need a medium, okay? Waves, okay, do not need medium to be transferred, and whenever the medium is optically denser, and when the medium is optically denser. What do I mean by optically denser? Who can send me on the chat? What's the meaning of optically denser? Optically denser, you heard about it in the IGCSE by another word called what? Optically denser, huh? I'll write it between brackets. Higher what? Higher refractive index. Excellent. Higher refractive index, okay? Whenever the medium is optically denser, it has higher refractive index, they will what? They travel faster. They travel slower, sorry. They travel what? Slower. Like light, okay? Whenever it travels from vacuum, it's the faster medium that the light travel through. Then as travel from vacuum, okay, to, for example, air, it will slows down a little bit. Then light slows much more through water, and through glass, it will be slower. And through diamonds, it will be much lower speed, and etc. whenever the medium is optically denser. So optically denser means, okay, it has what? Higher refractive index. For example, if we have water and oil and we put it in a cup, we know that water and oil do not mix. So the water will goes down and oil will rises up, because the density, mass over volume, the density of the water is greater than what? The density of the oil. But the refractive index of the oil is greater. That means it's optically denser than the refractive index for whom? For the water. So the light travels slower through oil than through water, but sound travels faster through water than through oil. So it depends on different idea. I'm not talking about density here, mass over volume. I'm talking about refractive index here, okay? So when we talk about mechanical waves, we are talking about density, but when we talk about electromagnetic waves, we are talking about what? Refractive index. And examples about electromagnetic waves, there are what? Light, bravo, and infrared, excellent. And we have much more, all the electromagnetic what? Spectrum, like X-rays, yes, exactly, and more, exactly, thank you. That's the first two types of medium, okay, two types of waves according to the need of medium, okay. I think that I answer your questions, okay, Muhammad and Shahid, okay, Muhammad, sorry, Muhammad and Shahid, I answer your questions. If you have any other question, you can send me on the chat, no problem. These are the first two types of waves, okay. Any question here? Okay, that's it. Good. The other two types of waves, depending on the direction of what? Direction of vibration. Direction of vibration. Direction of vibration. And since we are talking about something that you heard about it in the IGCSE and you already know it and you did the exams, okay, the externals, who can tell me what's the main words that describe longitudinal wave? Okay, if I want to describe the direction of its vibration, what's the main word that I have to write it down in my definition? Okay, to make them understand that, or to, that I understand what's the meaning of longitudinal, or what I can get the mark. Okay. Yes, thank you. Another answer. Yes, of course, it will oscillate, but both of these waves, they oscillate or they vibrate. But what's the main word, okay, that I have to write it down that makes a difference between longitudinal and transverse wave? Thank you. Another answer. Thank you, Shahid. Shahid, give me the correct answer. Another answer. Okay. Shukran. Muhammad, give me a correct answer also. I will not write the answer. Okay. Tamam. What else? You are welcome. Okay. Thank you, Shahid. Me too. So longitudinal wave, the waves, okay, which oscillate. What's the word? Parallel, exactly. Parallel to the direction of the wave propagation, parallel to the direction of the wave propagation. What do I mean by the wave propagation? Where the wave is moving, okay? The direction of the wave, okay? Propagation. That's the definition of longitudinal wave, which are the waves that oscillates or vibrates parallel to the direction of the wave propagation, parallel to the direction of the energy, parallel to the direction of the wave transferring, exactly. Transverse, I will use the same words, but not parallel. Okay, I would say not parallel, I would say perpendicular, exactly, perpendicular to the direction of the wave propagation, perpendicular. And as we know, here a good example, which is what? Sound. And here another example, which is what? Light and water waves. Okay, and many more. Okay, so for example, if I have a loudspeaker here, okay, if I have a loudspeaker, and that means if I turn it on for a certain type of what sound, you will see that the air molecules keep vibrating forward and backwards, okay, make a certain range of something called compression, okay, and other range of something called what? Rarefaction, where the molecules are away from each other and the molecules are close to each other. So that's range here, we call it compression, and this range we call it what? Rarefaction, and etc. Compression and rarefaction. So the molecules here, okay, the air molecules, they keep vibrating forward and backward, okay, forward and backwards, okay, parallel to the direction of the wave propagation. The wave is moving forward in this example, in this situation here, okay. While, for example, if we are talking about water waves, if this is the surface of the water when it's calm, okay, the vibrations of the water waves, it will be up and down, okay, perpendicular to the direction of the wave propagation, causes series of crests and troughs. So this point, which it's the highest point, we call it what? Crest, and the lowest point we will call it what? Trough. And the vibrations of these molecules are vibrating up and down, what? Perpendicular to the direction of the wave propagation. This is for the other two types, okay, of the wave due to the direction of the vibration. Any question here? I think it's clear and it's easy. Okay. If you have a question, you can send me on the chat. Let's move on. Okay. So we have something called progressive waves. They are the traveling waves. Okay. And these progressive waves, they travel, okay, and they transfer energy, not like standing waves. The standing wave, they don't move, they keep in their positions, as we are going to talk about them when we talk about musical instruments later on. So progressive waves are the waves that transfer what energy away from the source. All types of mechanical or electromagnetic waves, as they travel and they send the waves away from the source, they call it what? Progressive what? Wave. Tamam? Okay. So when we talk about the word oscillations here, okay, when we talk about the word oscillation, what do we mean by the word oscillation here? That means any vibration that repeats itself in a periodic oscillation, okay, periodic vibration that keep repeating at the same time, that's called what? Oscillation. That the oscillations, we are going to talk about it with more details when we talk about A2 physics, Cambridge or Edexcel. So if we have a spring and the spring here with a load, with a mass, and it keep vibrating up and down, okay, that's called oscillation, but not wave. Okay, maybe it would produce a sound wave. The same thing for a pendulum, as it's swing to the right, then back to the left to the same original position. That's also called what? Oscillation. Okay. The same thing if I have what? A slinky, a clamped ruler. Okay, if I have a ruler on one of a desk, as you was in the when you were young, and you put it here. Okay, this is the ruler. Okay, on the edge of the desk. Okay, you put your hand here and you release the other end. Okay, of the ruler to keep vibrating where up and down. Okay, these oscillation that repeat itself, it produces a sound whenever how long it is. Okay, so these oscillations, okay, that's the meaning of the vibrations, but all of these are not waves. They are vibrations that have the same period, same frequency, repeat itself. Okay, the same thing here. If I have a slinky spring and I oscillate it up and down to transfer the energy away from the source, in this situation I'm talking about waves. Okay, or even when I vibrate the slinky spring forward and backward to make the wave keep moving forward, also in this situation I'm talking about waves that pass through what? The slinky spring. Maybe I'm talking about transverse wave here, or I'm talking about longitudinal or longitudinal according to the accent, if it's American or British. Okay, tamam. The same thing as you heard before, maybe how the light come out, okay, how the light is transferred from region to another region, how the electric field or the magnetic field is produced. We know that as the electron oscillates, okay, and we are going to talk about that later in details, it produces both electric and magnetic field. And both electric and magnetic field, they are 90 degrees to each other, they are perpendicular, okay? And that's why they called electromagnetic wave. This is the light, okay? As the electron vibrate, it produces both electric and magnetic wave field that's transferred in all directions, produces something called what? Light. It depends on how many, something we are going to study it later on called photon, how many photons the electron release, how much energy does it have, okay, and how the light will produce, okay? So another important note that the motion that repeats itself over and over again, okay, we call periodic motion. So any wave, any oscillate that keep repeating itself in the same period, in the same time, in the same frequency, we call periodic what? Motion. Any questions so far? Any questions so far? Okay, so let's move on. So any wave, all the waves, they can describe by the following properties. What is the amplitude? What is the period? What is the frequency? Okay. And what is the wavelength of it? Okay. And finally, the relationship of all of these together by something called the wave equation that can find the relationship between the frequency and the wavelength with the speed. So we're going to talk about these, okay? in details, okay, now and later on, okay, and you'll realize that every time they ask about a question about waves, we have to talk about these words to describe things later on, okay? So what's the meaning of amplitude? Amplitude is the maximum displacement from the mean equilibrium position. So when the wave is oscillating up and down, okay, from the equilibrium position, what is the farthest distance that can be reached? This distance is what as the amplitude, going up or going down, okay, or going forward or going what, backward. And usually we use this word amplitude to describe how much energy we can carry out in the wave, okay? Clear? Next, period is the time for one complete oscillation, and the unit of it is in seconds. So any oscillation, any wave that keep repeating itself, okay, with the same time, if I know how to measure this time for one complete wave or one complete oscillation, we call period. And from this, we know that the period has a formula which is equal time divided by number of of oscillations. If you please write this down. So the unit of time is supposed to be in seconds, okay? To make the unit of period, also it's what? In seconds. So by using this, to answer this question, what they ask here, a spring oscillates 30 times in a minute, what is the period? So the time, it's a minute, and we have to convert it into seconds. So 1 minute multiplied by 60 seconds, okay? Divided by what? Divided by the number of oscillations, which is what? 30. So the answer is 2 what? Okay, 2, صح? Okay, I did 2 mistakes here. Who can tell me on the chat what are my mistakes, or give me one mistake? What is the thing that I did it wrong here? Thank you, Shahid. Okay, I'm talking about 1 minute, and each 1 minute is 60 seconds, not 1 hour. Okay, another one, another answer. Okay, I convert minutes into second, multiply by, I didn't write the unit. Excellent. One of the correct answers here, Bilal, thank you, Bilal. I didn't mention the unit on the final answer. The final answers must include the unit, and the unit is supposed to be in seconds. That's one of my mistakes. What is the other mistake? What is the other mistake? You are welcome. What's the other mistake? The other mistake that usually in physics, okay, especially Edexcel, okay, you have to write all your answers 2 or 3 what? Significant figures. Excellent. Okay, so that means I have to put 0.0 here, 2.0, okay, to get the whole answer. This whole answer is 1 mark. If I sometimes they will not give me the mark if I didn't put 0.0, 2 significant figures, okay? So I have to write the whole answer because I don't know the mark scheme, and neither you do. Okay, so during the exam, you have to be careful about writing the unit and writing the answer at least 2 significant figures, okay? Next, what's the meaning of the frequency? The frequency is the number of complete vibrations or oscillations happened every what? Every second. So that means the frequency equal the number of vibrations divided by what? Divided by time. Look here. Who noticed was the relationship between period and frequency? Yes, they are the inverse to each other. Exactly. So the time supposed to be in seconds. So that means the frequency, it will be in what? The unit of frequency is per second, which we call it what? Hertz, Hz. Exactly. So that's why the frequency and the period, they are the inverse to each other. So frequency equal 1 over period, or period equal 1 over frequency. Good? Tamam? Okay. So to do this question number 2, what they ask? A pendulum swing 90 times in a minute. What is the frequency? So frequency equal number of vibrations divided by time. So it will be 90 over 1. Is this correct? Aha, thank you, Shahid. No, it's not correct. What's the correct answer? What I have to do? Bravo. Who can give me the answer? What did I do a mistake here so far? I didn't convert minutes into seconds, so I have to multiply it by 60. Excellent. So the answer will be 1.5 what hertz. Exactly. 1.5 hertz. شكرا يا بلال. Okay. Next. تمام شكرا. تمام. في كثير answers بعتوا لي شباب. شكرا لكم شباب الصبايا. Okay. So question number 3 here. What do they ask? An oscillation of frequency 10 hertz was the period. According to this formula, the link of the frequency and the period are the inverse. So 1 over the frequency equal the period, and 1 over the period equal what? The frequency. So it will be 1 over 10. So the answer will be 0.1 what seconds. I have to put here another 0 to make it what? 2 significant figures. To make it 2 significant figures. Exactly. شكرا يا بلال. So always we have to know that the frequency of the wave is the same as the frequency of the source. What do I mean? The sound that you hear it, okay, have the same frequency of my vocal cords. Put your hands here, if you please. Put your hands here and say a word, for example, Bismillah, okay? What do you feel? If you put your hand here and you say any word, for example, your name, or say Bismillah, you will feel exactly. Thank you, Amira. What do you feel? Shukran. Muhammad. What do you feel? You feel vibrations. The number of vibrations that your vocal cords produce have the same frequency as the sound come out from your mouth. You have the same frequency as the source. So the frequency doesn't change unless we have something change. The same source changes, or something else that they remove it from the syllabus called Doppler effect. Okay, so yes, thank you, Sabah. You feel vibrations. These vibrations is the number of frequencies, number of vibrations happened, and you can't count it. It's very high. The number is huge. For male, it's approximately 800 to 1,000 vibrations every second. For female, it reached more than 2,000 vibrations per second sometimes, and that's too fast. No one can count how many vibrations unless you have a certain instrument to do that. Okay, so again, the frequency of the wave is the same as the frequency of the source, since the oscillating are directly caused by the oscillating what source. The last thing here, we have to know about something called the wavelength, which is the distance between 2 points are oscillating in phase. Later on, we are going to explain the meaning of in phase. But now on, when I'm talking about in phase, I'm talking about same time, same speed, same vibration, same position. That's the meaning of in phase. So the distance between crest to crest, or the distance between compression to compression, all these distances, they call it what? Wavelength. What do I mean by in phase? Now, a small introduction about that. For example, you know that in our culture here in Syria, Palestine, or Lebanon, okay, or Jordan, we have a lot of people that they do dabka, okay? They move and they hit the ground at the same instant, okay? If they are hitting the ground with the music at the same instant, that means they are in phase, that they are perfect. If they are not hitting in the same tune, in the same vibration, the same moment, they will not be beautiful, okay? It will be not dabka actually. So they are not be in phase, okay? It will be out of phase or anti-phase, okay? So later on, we are going to talk about in phase and anti-phase with more details, okay? So in this here, in this wave, how many waves can you see here? From this point to this point, how many waves we can see here? Who can tell me? Send me on the chat. Yes, thank you, bravo. How many waves? Bravo. No, be careful, Yazan, it's not your answer, huh? How many waves you can see here? Okay, thank you, Selma, huh? Bravo, ya Muhammad. Who else, huh? How many waves we can see here? We can see a wave until this point and a half. So wave and a half here. Yes, exactly, thank you. So in this wave, okay, this maximum vibration from the equilibrium position, okay, going up or going down, it's called amplitude. The same thing here onto the maximum position going down from the equilibrium position, also it's called what? Amplitude. But the wavelength is the distance from crest to the next crest. Okay, this distance, it's called wavelength, and they use, as you know from the IGCSE, the Greek letter lambda to represent the wavelength, or from the beginning of the wave to the end of the wave, we have a positive pulse and negative pulse. Also, this distance called what? A wavelength. Is that set, ya Ustad? No. Also, I told you the point that they have the same vibration. This point here, because it's after the crest by a little bit and going downwards, okay, the wave is moving to the right. And this point here, okay, also because they have same distance, the same vibration, same position, also the distance from these 2 points in the red color, it's called what? Wavelength, okay? Yes, the height of the wave going up or down, shukran sabah, called what? The amplitude. Any questions so far? These 4 transverse waves, if we go to see the longitudinal wave, for example, the particles, they keep oscillating forward and backward. This particle, for example, it was here, and it moves and vibrates until this point, and this is the maximum displacement. This is the maximum point that can move in this longitudinal wave. Okay, this is called amplitude. They never ask about it so far, but to make it more clear, because they put it in the picture, I put this one here. When there is no waves, these are the particles when they are stationary, they don't move at all. But when there is wave here, no waves, and here there is a wave. There's wave, okay? As you can see, the wave is moving, for example, to the right, okay? The particles, they keep oscillating where? Forward and backwards. So this particle reach this position here, and this is the maximum displacement that can reach it. That's why they call it what? Amplitude. It's the maximum displacement from equilibrium position. The same thing here. From here to here, this is the maximum displacement for this particle to oscillate. That's called also what? Amplitude. So the point or the region when they get close to each other, thank you, Amira, okay? The point or the region when they get close to each other here, they call it compression. And when they get away from each other, they call it what? Rarefaction. And the distance between compression to the next compression, what do we call it? The distance between compression to the next compression, what do we call it? Excellent. Bravo, huh? Who else? Ya salam, we call it what? Wavelength. Okay, so you have to be careful, okay, about the distance of amplitude and the distance of what? Of the wavelength. Now, it's not necessary to be from the middle to the middle. I can measure the wavelength from this edge here to this edge. That's why I choose these colors to make them the same things. So you realize that they are moving with the same vibration. That's why the distance is wavelength, okay? So the middle line, yes, you can call it, thank you, Sabah, what? The resting line or the equilibrium position. Bravo, thank you. For the transverse wave here, or for the equilibrium position at this point here, the black lines. Yes, thank you. In this moment, they are in equilibrium position, but after a moment, maybe they will not, because they keep moving. That's for what? For longitudinal wave. It's not like transverse wave. Transverse wave is more clearer. So again, for the wavelength, we determine what the distance that travel for the energy every 1 second for a period of time. And when for the transverse wave, as we vibrated at right angle, okay, 90 degrees, the wave is moving forward. That's transverse wave. But for longitudinal, we vibrated parallel, okay, forward and backward, okay, the molecules as the wave is moving away from the hand, okay, we keep shaking the hand right and left, so cause this series of compressions and rarefactions. Thank you. Shukran ya Amira, shukran ya Sabah. Any question here? Okay, let's move on. The same thing here, all the particles, they keep vibrating up and down, okay? And transverse wave, they keep vibrating up and down while the wave is moving forward, while, okay, and longitudinal, they vibrate forward and backward while the wave is moving what? Forward, okay? No problem, Yashad, thank you. So here is the same thing. We know that this region is called compression. When they get close to each other, the molecules or the vibrations of the slinky spring, okay, and this is called rarefaction. And the same thing here, we call the highest point crest and the lowest point what? Trough. All these informations, you know it from the IGCSE. Now we are going to use them again to explain more details later on when we talk about waves. So the most important equation here, okay, it's speed of any wave equal frequency multiplied by wavelength. Several times we are going to use this equation during the exam, okay? So can we derive this formula? Can we check if this formula is correct or not? Of course we can derive it. We know that speed equal what? Speed equal what? Distance over time, right? Distance over time. Yes, we know that since 4th grade that, okay, that this is the speed equal distance over time. But when we talk about a single wave, okay, when we talk about a single wave or one wave, the distance called the wavelength, lambda, and the time we called what? Period. Okay, if we are talking about what? Single wave. So, and also we know that the inverse of the period, because the period is written in the bottom, the inverse of the period, it's called what? Frequency. So that's why we can write this equation in this way: speed equal frequency multiplied by wavelength. And the speed is supposed to be in meters per second or centimeters per second, meters per second. If the wavelength are in meters and the frequency are in hertz. So the wavelength must be in meters and the frequency must be in hertz. So we can write the speed in meters per what? Per second. Any question here? Is it clear? Okay. Good news. But now, if I keep moving here and look to the next question, okay? The next question, what they ask: calculate the wavelength for A, sound, B, ultrasound. Now, sound and ultrasound, it's sound, but what's the main difference between sound and ultrasound? Send me on the chat. What is the difference between sound and ultrasound? Yes, thank you. Good answer. Who else? Both sound and ultrasound, both of them, they are sound. That means they are longitudinal. Okay, both of them, they are longitudinal. What's the main difference between sound and ultrasound? Maybe they have same speed through the same media. So no, the difference is not the speed. What is the main difference between sound and ultrasound? Let me show you something, okay? Let me show you something, okay? I have an application here called what? Dog whistle, okay? If I turn it on, you can hear a noise, okay? Now you can hear this noise since the vibrations are transferred from the microphone to you. It's yes, it's okay. So if I change the frequency to a very high frequency, okay, above a certain level, you can't hear it. Even me, I can't hear the voice. Also, when I reduce the noise, okay, to a certain frequency, lower than a certain frequency, also you can't hear what? The noise. Why is this? Okay, there's many applications that you can find it to change the frequency, okay, for some certain frequency that can't be heard. Exactly. Why we can't hear it? Because they can be ultrasound or infrasound. So what do I mean by this? So we can hear sound, but if we can't hear it, it will be called ultrasound or infrasound. So the main difference between sound and ultrasound and infrasound, that the frequency or the wavelength, the frequency. Yes, thank you, Bilal. The frequency, if it's too high above the normal range of hearing, okay, we call it ultrasound. If we can hear it, okay, I'm too old, okay, I can't hear all the frequencies as you are young people, okay. So we can hear from 20 to 20,000 hertz. Above 20,000 hertz called ultrasound. Below 20 hertz, it's called what? Infrasound. All human cannot hear it, okay? only special cases a human can hear it, okay, and other animals, okay, usually. So yes, exactly. So both of them, they are longitudinal sound or ultrasound. Let's go back, continue to read the question. The sound has a frequency of how much? 256 hertz, while ultrasound has a frequency of 2.2 megahertz. What do I mean by mega? Mega is a prefix, okay, that we have to know how to use it, like kilo, mega, giga, okay, santi, milli, micro. Exactly. شكرا يا نور. Yes, شكرا يا جهد. Bravo. Mega means million times 10 to the power of 6 zeros here, okay? So that's why ultrasound can't be heard, because it has too high frequency, okay? The range of a human can hear, okay? We can hear sound that we can hear it from what? From 20 hertz to 20,000 hertz, 20 kilohertz. That's what we can hear. Above this, it's called ultrasound. Below this, it's called what? Infrasound. So any sound above, we can't hear, and any sound below, also we can't hear. And whenever you get older, this range of hearing gets what? Shorter. Okay? Tamam? Okay. So again, sound and ultrasound, okay? If the speed of sound in air only 340 meters per second, but speed of sound or ultrasound through body tissue, it's faster, 1,500. Why it's faster? Because it's denser, the molecules are closer, so that's why the speed is faster, okay? Even sound, it has this speed, okay? So sound or ultrasound through body tissue, they have approximately 1,500 meters per second speed, okay? But through air, approximately 300 meters per second speed, okay? Yes, that's why the sound, they can pass through your body easily, because you are what the sound, it's mechanical wave and needs a medium, and whenever you are a particle, okay, you have many particles, that's why the speed pass through you faster. So in both ways, okay, we are going to use the same equation, speed equal frequency times wavelength, speed equal frequency times wavelength, and in both situations, wavelength, okay, is equal what? Speed divided by frequency, speed divided by what? Frequency, and you have to know how to use your calculator. So the speed, which is 340 divided by 256, and the answer will be 1.3 meter. That is the wavelength. But here, the speed of sound through body tissue is 1,540 divided by the frequency. As you told me, is mega, that means million. So 2.2 times 10 to the power of 6, and you have to know how to use your calculator. So the answer will be 7.0 times 10 to the power of -4, and the unit is what? Meters. That's why usually sound and ultrasound, okay, they have small what? Wavelength, okay? So we can hear it. If it's too small, like ultrasound, we can't hear it, okay? And whenever it's a smaller, it can detect, okay, by using ultrasound sonar, it can detect more details, as we are going to study later on, okay? Any questions so far? Any question? So you realize the difference between sound and ultrasound, okay? Here, okay, for any wave that we can't hear it, we called, okay, ultrasound, okay, it's above 20,000 hertz. Any vibrations below 20 hertz, they call it what? Infrasound. That means it's below 20 hertz. We can't hear it also. Okay. Usually I put questions as homework, and I assume that students send it to me in, privately on the WhatsApp group, okay? So we have, okay, okay, one of the questions, like ultrasound has lower wavelength. What does that indicate? It has a huge frequency. Whenever the wavelength is smaller, the frequency is greater, because they have the same speed. And whenever the wavelength is smaller, as we are going to study later on, it can be used, ultrasound sonar, to detect smaller details. Okay, that's why doctors, they use ultrasound to see what certain details inside your body. If it's very small, they can't detect it by ultrasound. They ask you to make X-ray scan or MIR scan. Okay, it depends on what the doctor wants to see inside your body. So as usual, I put homework questions for the student to check that they study. Okay, so question number 3, page number 8, and question number 4, page number 8 are homework. I want from you to send it privately on the WhatsApp, okay, to my number on WhatsApp. Okay, let's move on to question number 5. Question number 5. A sound has a frequency of 5 kilohertz. What that means? What's the meaning of 5 kilohertz? Exactly, 5 kilohertz means 5,000 hertz. Yes, times 10 to the power of 3. Okay, the speed of sound in air is 300 watt 30 meters per second. Before it was 340, now 330. Is there is difference here? Yes, maybe the humidity changed, the temperature changed, it doesn't matter. Okay, it's a small change here, but still in air it has a small speed, slow speed. Okay, so question 3 and question 4 are homeworks, exactly. And question 2, this is the answer for them. Okay, and the question number 1, we derive the formula speed equal frequency multiplied by wavelength. And whenever the wavelength is smaller, the frequency is greater. Okay, to make the speed is the same through the same medium, as we're going to talk about that later on with more details. Question number 3 and question 4 are homework. Question 5, a sound has a frequency of 5 watt kilohertz. Okay, means 5,000 hertz. The speed of sound in air is 330 meters per second. Calculate the period. Yes, who can tell me what's the formula for period? Period equal what? Yes, send me on the chat. Period equal what? Excellent, excellent. 1 over what? The frequency. 1 over the frequency. So 1 divided by 5,000. Okay, and the answer will be 2.0 times 10 to the power of what? Of negative 4 seconds. That means 20 millisecond. If they ask about millisecond, you have to know how to convert this value to this value. Okay, right. How do we know that? Yes, now we know that 20 times 10 to the power of negative 3. Okay, yes, excellent. Okay, طيب مش مشكلة خلاص. Later on. Okay, طيب. Part B, calculate the wavelength. Calculate what? The wavelength. Now we know that speed equal frequency multiplied by wavelength. So that means wavelength equals speed divided by frequency, which is 330 divided by 5,000. And the answer by using calculator is 0.066 watt meter. That's the wavelength. We did the question number 5. If you have any question, you can send it on the chat. Question number 6. What do we conclude, okay, about the relationship between the frequency and the wavelength for the same wave at the same constant speed? Now we know that, since V equal frequency times wavelength, that means frequency equals speed over what? Over wavelength. That means frequency is inversely proportional, exactly. Inversely proportional with what? With wavelength. Inversely proportional. Thank you, Amira and Noor. Okay, inversely proportional. And inversely proportional means what? As the wavelength decreases by a factor twice, 3 times, 10 times, whatever, by a factor, okay, not only decreases by a certain value, a certain ratio, by a factor, the frequency increases by the same factor, So they are inversely proportional. And as you know, what's the meaning of inversely proportional? As the first one increased by a certain factor, by a certain ratio, twice, double, triple, okay, 10 times. The other one, which is the frequency, will what increase by the same factor, double, triple, 10 times, okay? Because the speed remains constant through the same media. If the medium change, that's something else, okay? We are going to talk about it when we talk about refraction. Now, how can we demonstrate sound? Actually, this type of question, I don't know, they put it in the syllabus, but I don't know how they ask the questions about it. How we can demonstrate sound? We can put a flame, a candle, okay, in front of the loudspeaker, and you will see that it will flink as you turn on the speaker forward and backward. That means the vibrations are forward and backward. That's why the flame of the candle keep vibrating or flinking right and left, flinking. Okay, tamam. Or we can use what? A slink spring, and we keep vibrating it forward and backward to see the region where the molecules are close to each other or where the molecules are far from each other, etc. Excellent. And don't forget that we're talking about the longitudinal wave, which carries the energy away from the source. And these examples from where? From left to right. Good. Now, there's other types of waves that we have to know them, okay? If they write the word on it, okay, you have to know what the meaning of this word. For example, if we have continuous wave, okay, they never ask about it, but they put it in the book, okay? It produces, okay, it is produced by repeating disturbance that it moves from forever to wherever, and we don't know where it will be end. That's continuous wave, move to the right, to the left, or upward or downward in all directions, okay? And we don't know where's the beginning and the end of it. Train wave, we have several pulses, and we know where's the beginning and where's the end. Who can tell me how many waves we can see here? How many waves we can see in this train wave? Huh? How many waves? Send me on the chat. How many waves? Yes. Thank you, Amira. How many waves? Thank you, Shahid. Thank you, Bilal. Excellent, Bilal. You are correct answer. Thank you, Noor. Correct answer. Thank you, Salma. Correct answer also. Okay. But look here, we have one wave, two waves and a half. So here we have 2.5 waves. Whenever we have 2.5 waves or more than one wave, we call this what? A train wave. No problem, no problem. Okay. Now that's a train wave. Or we have something called pulse. Okay, these words we are going to use them later on. So what's the meaning of the pulse? It's okay, one complete oscillation, okay, that can be only one up or one down, one forward and one backward. This is called pulse, or this is called pulse, or this is called one wave, a whole wave. So all this, can we call it what? A pulse, okay? That means a complete vibration. Good? Okay. Also, we have to understand the difference between circular waves and what? Plane waves. Circular waves, even if we are talking about sound, 3-dimensional spherical waves, or we are talking about light, 3-dimension, okay, or we are talking about ripple tank, and we have ripples in circular wave, okay, they have a center here, a source, and these are called wavefronts, and these lines, what do we call them? These lines, these arrows that I just put them, what do we call them? Yes, thank you. We call them what? Ray. Okay, what do we call them? We call them ray. And each distance between wave to another what? To another wave, all these, okay, we call them what? Wave fronts. Okay, maybe they are crests, maybe they are trough, it depends on the angle. So we call them what? Wave front, okay? And the angle between the ray and the wave front, they have to be what? 90 what? Degrees. They have to be perpendicular, because the ray, it's going to show me the direction of the wave propagation. Why the wave front, it can be crest or trough. It's a line joining all points having the same vibration. Okay, and the distance between wavefront to another wavefront, who can tell what's the distance between wavefront to another wavefront? What they call it? Excellent, يا أميرة. What do we call them? برافو, we call them wavelength. Exactly. شكرا. مش هنادي أسماءكم كلياتكم. برافو عليكم كلياتكم أبعتوا أجوبة صحيحة. Okay. This is a circular wave and this is a plane wave. So for example, this is the wave is going forward, okay, in this direction. This is the ray. And all these represent what? A wave fronts, maybe they are crest or they are trough, okay? Wave front, okay? So, and the distance and the angle between the ray and the wave front, they have to be 90 degrees. And also the distance between wavefront to another wavefront, as you told me now, it's the wavelength, it's lambda. Okay. Now, a question, Heiko, for brainstorming question. Who can tell me when can plane waves be considered as spherical case of circular wave? At which circumstances or which condition we can assume that the plane wave, it's a circular wave, but it looks like a plane wave? Okay, I remember once when we was in a mosque here in Jordan, okay, in Amman. It's okay, when they put lines on the carpet to show me how we can stand in the lines for pray in the salah. Okay, I told the sheikh that these lines should be a little bit curved. He get confused and he didn't understand why I'm saying that. Okay, why we have to put them curved? Who can tell me why I have to put them curved? Actually, it's not that curve. It's negligible curve. Why? Because all of us, we are praying to what? To Mecca, okay, to Kaaba. And actually, when we are close to Kaaba, the lines there will be curved because they are part of a circle. But whenever we are far, it will be looks like what? Straight line, because it's a part of a whole what? Circle. It's a joke, okay? I was joking with the sheikh. So we can consider the plane wave when the source is too far. When the source is too far. So the curve seems to look straight at far distance. It's only a brainstorming question. They will never ask something like this. Any questions so far? Any questions so far? Let's move on. Okay, let's move on. Now, usually they give us graphs to describe motion, okay? And sometimes they bring questions about that, not always, not every year, okay? But we have to know a lot of things about the graphs, how we can represent the motion of any wave, okay? So first of all, we have to know something called displacement time graph, and we have to know displacement distance graph, or any other graph that represent the wave, even if it's transverse or longitudinal, as a sinusoidal wave, okay? So what that means, okay? We know that the sinusoidal sine theta, okay, can be changed from 0 degrees to 360, okay, to reach the maximum value at 90 degrees and minimum value -1 at 270 and looks like a wave that has a certain point in the equilibrium. The same thing for any wave. We can describe the displacement in centimeter or in meter, okay, and it can be a complete wave from this point to this point and etc. Who can tell me here how many waves you can see? How many waves you can see? Send me on the chat in this second graph. How many waves? Are you sure, Yazan? Are you sure, Amira? Thank you, Selma. Correct answer. Okay, thank you, Noor. Correct answer. Amira, fix your answer. Bravo. Shukran. Okay, we have a wave and a half. And as you can see here, I put here not degrees, I put here time, and T represent period. So a complete period, okay, that means a complete wave. So each one wave can be happened in a complete wave, and half wave can happen in what half a period, or quarter a period. It will be quarter wave, and etc. Vice versa. Okay, tamam. Good. So if we have two waves here, that's one of the wave is sine theta, and one is sine theta plus 90. Okay, that means one of the waves is in front of the other wave. So the red wave is in front of the blue wave, but by how much? By 90 degrees. Okay, now sometimes we are going to use degrees to represent waves. Other times we are going to use radians to represent waves, okay, as something called phase difference. Okay, later on we're going to talk about phase difference and what path difference in terms of degrees and in terms of wavelength, to compare between waves to make a relationship of something called interference and superposition of waves, or to reach something called standing waves later on. So what do I mean by phase? Each particle has vibration in the whole wave at different speeds or different direction, okay, different position. So each one has its own phase, okay? When the particles have similar vibrations and similar positions, we call them, they are in phase, okay? So the phase of an oscillation refers to the position within the cycle of the 360 or one complete period, okay, of the motion of the wave, okay? So if this is the displacement, it will reach a whole wave and a half wave like this. So what I can mention are the points that are in phase. They have the same vibrations. Who can give me examples for particles O, A, B, C, D, E, okay, and F, right? Okay, which of these particles, okay, they have same vibrations? That means they are oscillating with the same position, with the same frequency, with this everything. Okay, who can give me? Yes, thank you, Amira. Amira, give me a correct example. Okay, another example. Who can give me points that they are vibrating? Amira, no, this a second example is not correct. Okay, what are the particles or the points that they are vibrating in the same position and the same speed? Same position and same direction of speed. Okay, yes, thank you, Noor. Tamam. Okay, thank you, Muhammad, also. Okay, so look here. Point O, it's a one wavelength of point D. So if the wave is moving to the right, okay, and it will be something like this and keep moving, what that means? That means this point O, it will oscillate downwards from the equilibrium position, and also D, it will vibrate and move where? Downwards from the same equilibrium position. So I can say about O and D, they are what? In phase. Excellent. But I can't say that B and D are in phase, because B, it's moving where? Upwards. Okay, it is in equilibrium position as D, but B is moving upwards while D is moving where? Downwards. So B and D, they are out of phase, not in phase. Actually, they are completely out of phase, that they call it antiphase. Let's repeat. So we are going to talk about examples here. First, we have to know that the wave is progressive wave and it moves to the right, okay? And as it moves away from the source, okay, after a fraction of a second, the wave will be something like this, okay? That's how the wave will looks like after a fraction of a second. I don't know how much, after a certain period of time. Okay, what that means? That means the point O, it will move where? Downwards, okay? And point B, it will move upwards, and point D, it will move where? Downwards, and etc. And point F, it will move upwards. And all these 4 points, O, B, D, and F, are in the equilibrium position. They are in the same position, but they don't have all of them the same direction of motion. They have the same speed, the maximum speed, because E and C and A and E, C and E are stopping for an instant, then start to moving. Okay, for example, A is moving where? Downwards, while C is start to move upwards, and C start to move where? Downwards, and etc. So From all of these informations, okay, the direction of motion and the position, what I can say about these points? I can say that O and what? D, A and E, okay, B and F. All of these, they are moving at the same what? Exactly, they are in phase. Bravo, they are in phase. Why they are in phase? Because they have same position and same velocity. Let me write this down. Same position, okay, and same velocity. Velocity means speed and direction. Velocity. But, yes, but O and E, A, B and C, C and D, etc., E and F, they are out of phase by how much? By quarter wave. Let's say this a whole wave, this is a half wave, this is a quarter. So when we talk about a whole wave, which is 360 degrees, half wave, which is 180 degrees, quarter wave, which is what? 90 degrees. So they are out of phase by how much? Exactly by 90 degrees. So I'll write down this, okay? Out of phase, out of phase by 90 what degrees, because it's a quarter cycle. It's a quarter cycle. So they don't have the same speed, they don't have the same position. Quarter what? Cycle. Quarter cycle. While, look to this, while points like what? O and B, A and C, C and E, B and D, etc. Okay, all of these, they are completely out of phase. That's why they call it antiphase. What they call it? Antiphase. You can write it as one word or two words. Because they are antiphase, they are half cycle apart or half wavelength apart. Half what? Cycle apart. Okay, so that's why they are antiphase. That means they vibrate in opposite directions or in opposite positions. So we can write here opposite direction of motion, okay, or opposite what? Opposite positions or opposite positions. Opposite positions. Good so far? Is it clear? Tamam? Okay, take a screenshot or write these down. Okay. How is B moving upwards? Okay, طيب خلينا, let me repeat it another way because we are going to explain it later on several times. For example, if this is the wave and it's wave moving away from the source, it will move like this after a fraction of a second or after a certain time of a second. Okay, so that means all these particles here, they move where? Downwards, downward, downward, okay, from O to A. But these particles, they move where? Upward, upward, upward. And the fastest one will be B because it's in the equilibrium position, okay, until what? The speed is none, zero at A and zero at C. Is it clear? Did I answer your question? Okay, good. Tamam. You are welcome. Okay, write this down. Let's move on. So what I can say about what? So points on wave that are wavelength apart. Wavelength apart. Usually, what we are called them in phase. While those waves that half wavelength apart, half wavelength, okay, apart, usually we call them what? Antiphase. Maybe we are talking about points, maybe we are talking about waves. So it depends on the question, okay? So for example, here, similarly, if two oscillations are exactly set up like a dabka or like clapping the hands are in the same instant, in the same moment, in the same direction, okay, but one clap his hands with his whole arms, one clap her hands like gently like this, but in the same moment, in the same rhythm, okay, they are what? In phase, okay? Like these two waves, A and B. One is, okay, they are up crest in the same moment, they are top in the same moment, they are complete a whole wave in the same time, okay, or in the same degrees, they call them in phase. But if they are in opposite directions, or okay, they are the opposite, okay, like the peak and the troughs, they are in different times, like this wave A and wave B, the crests here and the trough here, they are in the same time, in the same moment. One is crest and one trough, or one is moving, okay, downwards and one is start moving upwards, and when they are in equilibrium positions, these whole waves, okay, not particles, they are called to be what? Antiphase. Now, whenever I'm talking about in phase or antiphase, I have to mention it in degrees, or I have to mention it in what? In radians, okay? So you know that a whole cycle, okay, it's 360 degrees, which is 2 pi in radians. The same thing, quarter cycle, it's 90 degrees, which is pi over 2, because pi is 180, half cycle. And 3/4 of a cycle is 270, which is 3 pi over 2. Right? 3 over 2 pi. Okay, pi is in the top, not in the bottom. Okay, good. Any question here? You have to know that. And always in the calculator, they have to be written in degrees. They ask questions in degrees, not in radians. Most of the, let's say all the times I didn't see question about radians, but let's say maybe most of the time, maybe they will ask question in radians. So far, they didn't do that. Okay. Is antiphase the same? Okay, the same as out of phase. Now, hold on. When we said, let's return back here, okay? When we said out of phase, 90 degrees, 40 degrees, 50 degrees, all this is out of phase. But if it completely out of phase, let me write it down here. If it completely out of phase, it will be what? Antiphase, completely out of phase, okay? We call it what? Antiphase, and that means the angle, it will be how much? 180 what? Degrees. Good? Clear? Okay. Now, the other thing, you are welcome. The other types of describing waves or particles when they are oscillating, they are not the word phase, they are the way path difference. So we have to know the relationship between phase difference and path difference, okay? So for example, phase difference, the relationship between what? Oscillations. It's not a definition, yes. Between oscillations in degrees. Okay? That's called phase relationship. But path relationship or path difference in terms of what? In terms of wavelength or lambdas. Yes, exactly. Yes. Okay. One of the things that you have to know it, but does not include, they will never ask about it in the past paper, that for example, if I have identical springs and they are what start to oscillate and they oscillate like a wave, okay, as this, they are oscillating as a wave. One of the things that we have to know that This particle here, for example, A, this is B, this is C, this is D, okay, and this is E. This particle A, it has the maximum speed going where? Going down, for example, okay? And E also have the maximum speed going where? Going down, while C has the maximum speed going up. Why I'm saying maximum? Because they are in the equilibrium position, in the middle, exactly. While B is it's at rest, okay, and start to move down, okay, and D it's also at rest, okay, because it's in the peak downwards, okay, or at the peak upwards, and start to move where? Upwards. So that's why all of these, okay, A and B, A and C, A and D, they are out of phase. But A and E, they are what? In phase, since they have the same what? Speed and same direction of motion and same position. While B and D, who can tell me about B and D, what they are? Send me. Okay, what about B and D? Huh? Yes, they are antiphased, exactly. Who can tell me about A and C? A and C, are they in phase or they are antiphase? Excellent, they are also antiphase. Excellent, excellent. So from this, quickly, I'll repeat it in a different way. A is out of phase with B by how much? 90 what degrees, okay? I'm talking about degrees yet, still, okay? So because I'm talking about degrees here, okay, I'm talking about phase, okay? The same thing when we talk about what? Also, we can talk about B and C here, or what? C and D, etc. But if I'm talking about, for example, A with C, A with C is what? Completely out of phase, completely out of phase. Okay, that means they are what? What we can call this? Exactly, we can call them antiphase. Excellent. We can call them what? Antiphase. You can write this one word or two words, antiphase. Like whom? They are antiphase. Like also what? Excellent. B and what? And D, or what? Or C and E. C and E. Okay? Etc. Yes, etc. Bravo. شكرا. صح. A and D are what? Are 270 degrees out of phase. Out of phase. A and D, they are 270 degrees out of phase. Like whom? Who can give an example like whom? Like bravo, B and what? E. Excellent. Okay. تمام. How to find the wavelength from displacement time graph? You said displacement time, so the time can find the period. If I know the speed, I can use the equation frequency times wavelength, and I know the relationship between frequency and period. They are the inverse. Okay. Tamam. There is a question like this later on. We are going to answer it. Tamam. Okay. Let's move on. You didn't understand what, Yazan? Okay. Now, from now to 4 weeks from now, we are going to keep talking about the meaning of phase from while to while until we understand what's the meaning of phase, because actually we're not going to write the word phase. We are going to use that to explain other things, okay? So for example, here he is. In this figure below, okay, in this figure here, okay, are points O and D in phase? Tell me, Yazan, are they in phase? Are they? Yes, why they are in phase? Bravo. Why they are in phase? Because they have same position and same what velocity, right? Yes, since they have same position and velocity. But this answer is not in the mark scheme. The mark scheme, we have to write what? We have to write, and they are, that's what we're going to focus about. And they are one wavelength apart. So we are starting to talk about something called path difference. So when we want to explain the phase difference, we will use the path difference to explain it. And when we want to use to describe the path difference, we are going to use the phase difference to explain it. So in the mark scheme, you are not going to write, since they have same position and same velocity. You are going to say they are wavelength apart. Good. Fine. Our points A and C are the points A and C. Antiphase are the point A and C antiphase. Send me the answer. Are they antiphase? Why they are antiphase? Yes, they are antiphase. Why they are antiphase? Since I told you before, let's go back, again. Here, we said that they are antiphase because of one of two reasons. Maybe we can say they have opposite directions of motion, or they have opposite what position. Here we have both opposite direction and opposite what direction of velocity. This particle, it starts to move downwards, for example, and this particle starts to move where? Upwards. So they have different what positions, okay? Since they have opposite positions. But this is not the answer in the mark scheme. What's the answer in the mark scheme? And are half wavelength apart. This is the answer, half wavelength apart. So actually we are going to use the term phase and the term phase difference to explain things later on, not the position and the speed as I start to explain. I start to explain it now so we can understand it more. Thank you, Shahad. Bravo عليك. صح. Shahad, give me the correct answer and correct explanations for both A and B. Bravo, ya Shahad. Okay, so write these down if you please. You are welcome. Okay. And let's move on to this question. بلشنا هلا بالجد. This is a past paper question from old syllabus. Okay, what they ask. Waves are sent along a slinky spring with a velocity of 0.25 meters per second. The diagram shows how the displacement varies with the distance along the slinky spring at a moment and a time. The wave is traveling to the right. The wave is moving to the right. So like this, after a fraction of a second, it will look like this. Okay, it will look like this. Tamam. State the wavelength. State that means you already know the answer. Calculate the period. Then what? Sketch a graph for the displacement. All these questions, okay, question number 2 and question number 3, in these 2 pages, we are going to answer them later on. That's it for today. We finish our time. We are going to continue it next period. If you have any question, you can